Welcome to today's lecture on fluid inclusions in minerals. We are in the middle of the second module, where we have been discussing about the principles of microthermometry of fluid inclusions, because microthermometry is the very basic source of information. By using a microscopic heating freezing system like the ones we described, they give us the bulk of the fluid inclusion data and the only source of data by which we can constrain the thermal regime of the fluid that we are interested in through our study of fluid inclusions in minerals. So, in the last class we were trying to just visualize the situation in which aqueous inclusions, what we see them in room temperature as either aqueous biphase with a liquid plus vapor combination, or aqueous polyphase, the liquid plus vapor plus a daughter crystal, which is a product of the post entrapment change in the inclusion cavity, when the inclusion has behaved like a closed system without addition or subtraction of component with the surrounding, exchange of component with the surrounding. And we at this point of time we have some basic idea as to the entrapment process. So, that provides the basis for the microthermometry of the fluid inclusions. The other common type which we discussed three types: the aqueous biphase, the aqueous polyphase, and the two liquid plus vapor type of inclusions, and where the other. So, it is essentially the fluid, the original fluid was a mixture of water plus non-electrolyte species like carbon dioxide. We are not taking any other non-electrolyte species to consideration right now, when we are dealing with the very simple cases. We very commonly observe fluid inclusions which have got an aqueous liquid plus a carbonic liquid and a carbonic vapor combination at room temperature. And we also please note that we also do see inclusions which are monophase at room temperature, means just looking like a liquid or a vapor, monophase. And such kind of monophase inclusions under some special conditions could be aqueous inclusions, because of certain situations which we will discuss later. Could be a situation in which the vapor phase has not been able to be nucleated, or the entrapment process took place at such low temperature that the vapor phase inside the inclusion could not nucleate. We will discuss such cases later, but coming to the situation in which the liquid that we are talking about, a homogeneous liquid or a homogeneous vapor, is carbon dioxide, which is very possible and is abundant in anywhere in the crustal segment. Depending on the environment, we can get carbon dioxide in the liquid state or a vapor state, and such kind of liquid carbon dioxide or vapor carbon dioxide inclusions get entrapped in the minerals which are either primarily growing or recrystallizing at any other point of time. So, the diagram here shows almost analogous or identical to the kind of diagram which you saw before for pure water. This diagram is a diagram for pure carbon dioxide. Just as you have seen before in case of water, this is the liquid vapor coexistence of carbon dioxide. The carbon dioxide triple point occurs at minus 56.6 degrees Celsius, and the critical point occurs at 31, it is not a minus, it is just the dash, 30 plus 31.1, 76 bars, and this takes place at minus 56.6. Now, with the help of this diagram, let us try to explain how pure carbonic inclusions could be occurring in minerals that we see in the room temperature in the laboratory, and what possible situations, what are the two possible situations. Let us say that exactly as if we have understood it properly. So, here this is the one phase liquid carbon dioxide field, and any point on this liquid, the density is uniquely fixed, and also the values of density at the identical points on the density till the point that it intersects the boiling curve is also uniquely defined, and this is also is an isochore for a carbon dioxide liquid. And similarly, these three isochores which are shown here are the isochores with decreasing density, and which we can represent as say rho, it's gram per cc in its unit. And let us say that we had two situations corresponding to in situation 1 and situation 2, where the situation 2 is a corresponding is representing a liquid where the density is a little lower and it was trapped here. If it was trapped here, it has followed the isochore and has intersected the boiling curve over here, and further since it happened to be conditions higher than the conditions prevailing at room temperature pressure. So, the star represents the point at which the star represents the room temperature pressure condition. So, this in this fluid which was trapped at 2 is likely to be present in the form of liquid plus vapor, liquid plus vapor, both it's carbon dioxide only, carbon dioxide liquid and vapor. In contrast to that, say the inclusion which is a little higher in its density and was trapped at a point corresponding to here at 1. So, that was also following the isochore, but the point which is the precedent temperature condition which is here is corresponding to this particular point that we can see. So, now this particular inclusion has not been able to intersect the boiling curve. So, this will remain as a liquid, this will remain only as a liquid and it will be monophase. Here this is a biphase, this will be monophase condition. Now, what will happen here if we see this when we see this inclusion at this particular point as a monophase, and if we decrease the temperature, because if we are using if it is put into the heating freezing stage where the temperature could be lowered below the room temperature, a slight lowering of the temperature and can make it change from a monophase to a biphase condition. So, a vapor bubble will nucleate as and when we decrease the temperature from room temperature by a few degrees. It could be how much or how much we should lower will depend on what is the density of the originally trapped carbonic liquid was. So, this explains the occurrence of pure carbonic inclusions either in monophase or in biphase condition, and also it would be worth noting here that such kind of situation which is very common and in most of the cases they are pure carbon dioxide, but in many cases in many instances this particular carbonic the carbon dioxide liquid is not pure, but sometimes is mixed with variable proportion of other gaseous species such as methane, with which it is miscible in all proportions and which doesn't and they do not have any non ideality, and we can see that. So, similarly we can also look at how to have an idea about the composition. Okay. So, now come to the situation that we discussed before is the mixed aqueous carbonic inclusions. means we will have a aqueous liquid, a carbonic liquid and a carbonic vapor. So, we have to explain that how such kind of a thing can happen. Similarly, we are in the subcrustal condition, and we also go by our basic assumption that the fluid is in one phase condition, and since it is a mixture, we can always represent it as a binary of in a binary diagram the way it is presented here between water and carbon dioxide. This curve is, as we all know, this is actually is something which you can call as a solvus. This is this curve is a solvus. So, solvus means it separates the fields where it will be a one phase liquid field, and in this case it is two liquid, means it is an aqueous liquid plus a carbonic liquid. So, whether the carbon dioxide part will be liquid or vapor will be depending on the conditions corresponding to the liquid vapor equilibrium curve for the carbon dioxide. But for the time being, we can look at the simple situation where it is a the solvus separates the one phase liquid to two phase liquid. So, similarly, we can always talk about a situation where the entrapment. So, this represents this field, a vast field in which a one phase fluid will be present, even though it is a mixture of carbon dioxide and water, it will be one phase, and either it could be supercritical gas fluid or it could be a liquid, depending on. So, what is shown here is the critical point for this particular mixture. And so, if we have a inclusion, if we consider a situation somewhere here corresponding to a pressure temperature P1 and T1, and if there is an inclusion which is trapped here, and we are decreasing the temperature, if the temperature is decreased, then exactly following the rule that we generally have for splitting up this particular liquid into two components, here and here. So, this particular inclusion, which was the inclusion fluid which was encapsulated in the host mineral as a homogeneous aqueous carbonic fluid, after its entrapment with decrease in temperature, when we will come to pressure later on, a decrease in temperature will intersect the solvus, and as it intersects the solvus, it gets splitted up into two components, an aqueous liquid and a carbonic liquid, and it will be present exactly the way we are presenting, that it will be an aqueous liquid and this will be carbonic liquid. So, this carbonic liquid, so exactly after the entrapment process, since the pressure and temperature is decreasing and also the differential contraction of the liquid with respect to compared to that of the host solid, there will be still, so a vapor bubble will nucleate, and that vapor bubble will be a carbon dioxide vapor instead of an aqueous vapor, because the it is basically the separation of the carbon dioxide vapor which will accommodate the staying in the volume, and it is always a carbon dioxide vapor. So, this explains the entrapment condition of a homogeneous fluid which is water plus carbon dioxide to the post entrapment change and giving rise to aqueous carbonic inclusion. Now, the solvus represented by red line, say suppose it corresponds to a pressure which is P 1, which is P 1. The one which is represented by the green line is P 2, and we can see that P 2 has a much larger immiscible region under it, field of immiscibility. This field we can always say that it is the immiscible region, and this is the on above it is the miscible region, and the orange one is corresponding to a pressure as P 1 and the green one is P 2, and a third one, this blue one, is P 3. So, as it happens, the phase behavior that the way we have studied, so P 1 will be greater than P 2 is greater than P 3, means this solvus which gives rise to the splitting of a originally homogeneous aqueous carbonic fluid will always be much easier, or the immiscibility will be achieved at a much higher temperature if the pressure is low. Means if the pressure is higher and higher, then the one phase region is expanding, the one phase region is more dominant, or the reverse, that the immiscible region expands with decrease in pressure. And as we know, the solubility of, because it is essentially coming out from the mutual solubility of carbon dioxide and water, because water is a polar molecule, carbon dioxide is a non-polar molecule, and there is a lot of high degree of non-ideality in their mixture, and their miscibility is very restricted, and lower is the pressure, higher is the immiscibility. So, this will be, so on the basis of this entrapment of a homogeneous aqueous carbonic fluid and the change in the post entrapment change in bringing about the phase separation is explainable on this basis of this diagram. It is also possible that as we have said, that we are not considering any of the conditions corresponding to heterogeneity in the fluid during the time of the crystal growth, which always is possible in case of the pure aqueous system, in which we have a boiling curve on which liquid and vapor coexist. So, heterogeneity is possible. Similarly, in this case the heterogeneity is also possible on those solvi, the discrete solvers which we have shown at different pressure. So, this actually defines the change at the critical point with increasing pressure, and this dotted line, the loci of it is the trajectory of the critical point, and this solvus is inherently asymmetric, and as you see that the mutual solubility of the carbon dioxide solubility in water is a little bit more than that of the reverse, that is the water solubility in carbon dioxide in the two extreme ends. Well, these photographs actually are showing the situation. On the left side photograph, we see that this is an inclusion, aqueous carbonic inclusion. It is occurring in its two phase condition. This is the liquid carbon dioxide and this is liquid water, and as you could see here, the one which is here is out of focus. On the next, on this diagram to the right, this inclusion is out of focus and this inclusion is on focus. Now, if we see these two, which are very much in the host crystal within the part of the occurring as a part of the random 3-dimensional network, you could clearly see that the proportion of carbon dioxide in this particular case is perceptibly more than that, or even the taking into the uncertainty of the third dimension into consideration, still we can say that this particular inclusion represents a higher proportion of carbon dioxide compared to the one which is here, which is occurring in a triphase condition. We can clearly see the liquid water, liquid carbon dioxide and the carbon dioxide vapor. So, it can be explained on the basis of this diagram, depending on the where if the composition is on the carbon dioxide on the water rich side or on the carbon dioxide rich side. If it is on the carbon dioxide rich side, then decrease in temperature will give rise to the splitting, where there will be this could be all calculated by using the standard Lever rule as we follow in case of binary diagrams, and depending on the composition being either somewhere here or somewhere here, then they are going to give rise to inclusions which will be aqueous carbon inclusion, showing their typical they can also be called as in a way a polyphase, means liquid, two liquid and plus or minus vapor. Such kind of entrapment process are very much possible and can be explainable on the basis of simple phase diagram. And we are still sticking to very simple situations, and we will discuss the more complicated ones later. Well, as just going a little further from a pure carbon dioxide, we also can take into consideration the fluid being charged with methane. So, it will be essentially carbon dioxide plus methane. And also at the same time, so the previous diagram was in respect of the entrapment conditions, which is at a higher temperature. Again, we will also be talking about the compositional characteristic. So, we talk about a pure carbonic phase, we talk about composition in terms of what other gases could be possible. So, it is in most of the cases this CO2 and CH4 are the dominant ones. One can also have situation like there could be some amount of H2S, sulfurous species, could be nitrogen, could be argon. So, these are the kind of gaseous species which are detected by analytical equipment, and sometimes also can be studied by the phase behavior in the fluid microthermometric experiments. This is one small example that I am showing here. What's being shown here is exactly the triple point of carbon dioxide, which is minus 56.6, and this green curve which is handwritten and is not to the scale, and this is the critical point. Okay, so this is the critical point Cp of carbon dioxide. This is the triple point of carbon dioxide, and as we know that the liquid vapor coexistence takes place anywhere in these pressure temperature conditions. This corresponds to about 76 bars, and this still lower pressure, and here the orange one. Okay, so this one, the black one, is also similar curve for methane. So, methane actually is a gas whose triple point is about minus 182.5. So, as you can imagine, when we are using devices where the temperature can be brought down to only level of minus 196, it is not possible, for reasons which I will explain later, it is not possible to obtain the critical the triple point of methane. Most it is very hardly it is possible to observe, whereas the critical point of methane is minus 82.1, which is easily observable, means any kind of a liquid vapor homogenization. So, here on this a pure methane, if we consider a fluid which could be a pure methane, then the pure methane liquid vapor homogenization or the coming to one phase is possible up to minus 82.1, after which it will be a supercritical gas, as we all know in case. So, all these individual species, such kind of phase diagrams can be constructed. Critical, because this critical density of carbon dioxide is about 0.4 grams per cc, and you can also have a critical isochore for the carbon dioxide as well as a critical isochore for methane. So, now why this diagram? This diagram only tells that, well, if the fluid is mixed with methane, if the carbon dioxide, so that means whenever we get a pure carbon dioxide liquid inclusions, if we are decreasing the temperature going to below temperature which is minus 56.6, then we know that the carbon dioxide is pure. If the temperature, so that means exactly here what is going to happen, since the triple point is solid, liquid and vapor coexistence. So, if we increase the temperature, then solid is going to melt and we will only be getting liquid plus vapor. So, now since if we get the melting taking place exactly at 56.6, then we know that there is no other gas which is mixed with it. Whereas, if it is mixed with some amount of methane, then this triple point of carbon dioxide is going to get depressed to variable values, even it theoretically can go up to minus 182.5. Similarly, if we have that particular carbon dioxide inclusion which is present as a liquid plus vapor inclusion, and it shows critical homogenization, that means which we will also discuss later on what exactly critical homogenization is. But for the time being, we can consider that the density of the carbonic fluid was such that it is exactly corresponding to the critical density. And then under that kind of situation, if we find that the temperature of homogenization of the carbonic liquid is lowered, then exactly what the way we saw for water and sodium chloride having a continuous critical curve. So, the this also can be say as a CO2 CH4 critical curve. Even if it is not a critical homogenization, if the homogenization happens to be if it happens to be a fluid where it mixed with carbon dioxide fluid which is mixed with methane, its temperature of homogenization is also going to be depressed corresponding to or compared to what it would have been if the carbon dioxide would have been a pure one. So, this kind of diagram give us some insight to understand the behavior, the response of the inclusion fluid to heating and freezing for understanding their compositional characteristic. So, this diagram is kind of a combined unary methane, carbon dioxide, water and H2S. So, it is possible that the way it has been drawn here. So, this is methane. Methane is minus methane is minus 182 degrees Celsius, the triple point, and this is the critical point of methane corresponding to minus 82.45 degrees Celsius temperature and 45.8 bars pressure. And this one, as we discussed just now, this is the methane carbon dioxide critical curve. Carbon dioxide critical point is at 72.9 bars and 31.05 degrees Celsius. We have a continuous critical curve for carbon dioxide methane, and it is possible to calculate the concentration of methane in terms of mole percent from such kind of depression in the critical temperature for carbon dioxide, or even the change or the depression in the homogenization temperature of carbon dioxide liquid if it contains methane. And this one interestingly is for H2S. H2S has a triple point which is lower than that of carbon dioxide. It has a critical temperature which is about 100 degrees Celsius and 90 bars, and this is carbon dioxide. So, even carbon dioxide and H2S are also miscible, and there is no non ideality, and there is no immiscibility in their in the phase relation, and you can also have a continuous H2S and carbon dioxide critical curve. So, sometimes when we find that the critical temperature, so the significance of this diagram is that if the carbon dioxide is mixed with methane, then there is depression in its temperature of homogenization or the critical homogenization, whatever the case may be. In case of it is charged with H2S, then there is an elevation or the increase in the temperature of critical homogenization or the homogenization temperature of. Sometimes it is reported that a critical homogenization of carbon dioxide is more than what it is what should have been the pure one. So, at that point of time one can suspect that there could possibly be some amount of H2S which is mixed with it. And for your reference, here the boiling curve for water is also plotted. Here this is the critical point of pure water, which is 218.2 bars, 374 degrees Celsius. But since we have a lot of immiscibility in the carbon dioxide and water system, we are not, there is no much of significance in seeing the critical, there is no continuous critical curve, but sometimes we do see such kind of a relation. This is temperature and pressure. If this is the temperature, this is the critical point of water, which is 374. With increasing carbon dioxide, we find that we can trace the critical curve up to a certain percentage, certain value of the concentration of carbon dioxide in the water. So, it only so these are the these simple phase relations, without getting into much more of the analysis of them, any rigorous thermodynamic analysis, these simple phase relations are at the back of our mind when we are studying fluid inclusions, doing microthermometric experiments, recording observations on different types of phase changes that we see in the fluid inclusions during freezing and as well as heating. So, heating runs generally will be conducted to obtain the condition corresponding to homogeneous fluid, because abiding by our or conforming to the very basic assumption of homogeneous entrapment. So, we conclude the discussion today here. Thank you very much. We will continue discussing in the next class.